Hello all, welcome to another session of EMCH 578 or 744 aerodynamics. So we are going to have a very small short tutorial on how to set up a mesh or grid system and analyze it in Fluent. We are going to analyze a simple airfoil, and I'm going to guide you through different steps of how to find the data points for that simple airfoil, how to analyze them, how to create a CAD model for your Fluent, and then eventually how to analyze them. And we will have different points and tricks throughout the way, so make sure to follow the tutorial. There are millions of other tutorials online. You can also like Google whatever question you have, or reach out to me through email to get your questions answered. So the first step of the way is to find the data points for an airfoil. For an airfoil of which you're choosing, there are two main websites that provide the data points for you. One is UIUC airfoil database, and this one you can go over this different airfoils as you can see, and it will give you a DAT file with a couple of data points for an airfoil on it. The other one is airfoil tools. There are other websites as well, but I mainly use these two. So airfoil tools is I don't want to say more comprehensive, but it gives you more freedom in the number of data points you want to generate, the type of airfoil you have, and all of those things. We want to use this type of airfoil here, NACA 4-digit airfoil generator. Here you can set the max camber as a percentage of the chord, max camber position, at the again percentage of the chord, thickness, and number of data points. I'm not going to change any of this, and this is going to give me NACA 2412. That's the first digit here. It stands for the percentage of max camber. That's percentage of the chord length, right? The second number here, 4, is the percentage of max camber position from the leading edge multiplied by 10, and the last one is the thickness of the airfoil, third and fourth digit. Let me increase the data points to 200 and then plot this again. You don't need to change any of this except for this one. You want to have a closed trailing edge. Essentially you want to start from here and then you want it to come back to here, right, to the same point. So let's plot this. You have the data points here. What I'm gonna do is get the data points, copy them, and as you can see we started from 10, then ended at 10 as well. It is a very important point when it comes to your CAD modeling. Let's come here, let's start a new text document. I'm gonna name it airfoil. Open it and just copy whatever, paste whatever you have copied here. Save it and close it, and then open Microsoft Excel or any data manipulation software you use. I use Microsoft Excel. You want to open a blank one, then go to open and open the file you just saved, the text file. All files, airfoil. You want to keep this delimited, and you want the delimiter to be a space. So it will give you all of these values, all of these numbers in one a small essentially part of this table. Okay, next and finish. First thing you want to do is to insert a column and a row. In the first column you write pound sign group. That is going to identify the group of these data points you're going to import later on in Ansys. And here you want to identify the point numbers. So pound sign point, identify the X direction, Y direction. This actually has to be and then Z direction. This is the special format you have to follow when importing files to CAD models in Ansys, right? It's a two-dimensional, it's an airfoil, so it's two-dimensional. We only have to have zeros for this. Point numbers, you want to start from 0 and then 1, 2, 3, 4, and then this will add all of it. We are going to have 200 points as we said, and again it's a closed airfoil, so we start from the trailing edge, go to the leading edge here, and then go back to the trailing edge here. And the group, you want to name it group 1. So this will give you all of the data points you need to import an airfoil in an Ansys CAD model. You can definitely input all of these data points individually in the Ansys CAD model, but you don't want to do that. That's going to be time consuming, and if you only add like 10 data points, it will bring down your accuracy of the mesh of the grid points. Okay, so just save this again as a text file, and we're gonna come and open the Workbench. If you don't know where to download the Workbench or Ansys Workbench, please reach out to me. I will guide you through the correct path essentially. Keep in mind that you can download the free version of Ansys, a student version of Ansys, from their website, the Ansys website, but we also have Ansys installed in the computer labs. And there are a couple of labs in each computer lab that designated for online students. So if you don't know how to access those computers, please reach out to me. And if you're on campus, you can use those. The difference between the installed version we have in the computer lab and the student version, which I'm running right now, is the number of data points you can have. So if you want to increase the number of data points in your mesh, it is better to use the computer labs. And they have very powerful computers there, so I would definitely recommend using those. So this is the Workbench area. When this is the first thing you see when you open Ansys Workbench. You have millions of different models, not literally millions, but a lot of different models that you can use. We have in this analysis system, we have coupled, field harmonic, all of these like modal analysis, static analysis, buckling analysis. But what we are interested in is the fluid flow analysis. They have different softwares for fluid flow analysis, as you can see here. And we want to use the Fluent one. So I'm just going to hold and drag this here, and we'll give you a standalone solver. Here you can define the geometry, mesh, set up solution, and see the results as well. We could have done this separately. You could have come to this component systems and then create a geometry. I'm going to do the standalone here, then add a mesh to it, and then add the Fluent analysis on top here. Okay, but we already have all of these, so we don't really need to do it separately. I'm just going to delete all of these to avoid any possible confusions. And to delete any module, you can just come here, right click and delete. So let's start with the geometry. Before doing the geometry, if you are someone who is more comfortable with working with Excel, you can definitely create a whole wing with this Excel. You just have to do some manipulation on these numbers. For example, if your wing is a rectangular simple wing, you just can copy all of this and add your span length here. What I mean is this. Let me copy all of this down here. We don't want to copy the data points, so you have to make sure that data points here, if you are doing this, the data points should go from 201. Let me actually delete this to avoid any confusion. Okay, so here we have another set of data points for airfoils. And if you know your span length, let's say your span is 2 meters, and just add a 2 in your z direction, and you will get the full data points for a wing, with a rectangular wing with a span of 0. But this part is a little harder, dealing with the data points, especially if you are dealing with a wing that has a variable chord, or it has a twist, or any type of like non-rectangular wing. So it is better, in my opinion, it is better just to stick to this, to the airfoil data points here, then do the rest of analysis in the Ansys system. So first part is geometry. There are 2 different geometry or CAD softwares in Ansys. There are more than 2, but the 2 standard ones. This one, the first one is new, is Space Claim. The second one is the design model. We are going to use the design model. Design model is a little easier to understand and figure out, and it's an older software, so maybe I'm just getting old. That's why I want to use my the software that I've used before. So let's open the design modeler. Of course, it takes a little bit of time to open depending on how fast your computer is. This is going to be your design model environment. What I'm gonna do now is to import the data points we have already created. So you come to concept here, and it is going to be a 3D curve. We are going to import this 3D curve here. It tells you that how do you want to define this 3D curve. We are going to use the coordinate files, but we can actually define points and just select point to create a 3D curve. When you say you want to use a coordinate file, it will give you this coordinate file option. I'm just going to come here, go to desktop where I had the coordinate file, and then I think this was, yes, airfoil. I'm going to open this, and then your coordinate unit is in meters. Your base plane is XY plane. You can see the base planes here. XY plane is going to be our base plane, and we don't want to add any material here. We can do that later on, and then generate. This is the data points that you can see in your design model. Next step is to create a surface from these curves. Okay, so you see the surface here. Just come and click on the surface, and then click on the apply here. So you're choosing the edge you want to create the surface from, and then generate. If we didn't close the trailing edge when we were creating the airfoil tooth here, if we didn't do this, essentially means that if we don't have these 2 points as the closing and the starting and the closing points, the same points, then we couldn't have made this surface. We should have added a point or created a separate edge manually. So we have an airfoil. That's the first step. The second step is to, let's consider this as the root of the wing. We want to do a 3D wing. If you are doing a 2-dimensional wing, this is it. You can stop here and go create your mesh. You have to have an enclosure, but we'll talk about those later on. If we want to do a wing, so we are going to create a new XY plane, a plane, right? By click on this here, and then make sure that it is not on the same plane that we have already created. So we have to transform it. We have to offset it in the Z direction, and this offset is going to be your span length. I want to keep it simple, so I just want to keep the span length as 1 meter, which is a very small span. So this my span length right now is essentially the same as the chord length, which is very small. So see, we have a plane here and we have a separate plane here. So on this plane, we are going to create another 3D curve, essentially import data points. We don't want to do point selection. We want to import from coordinate files, and on coordinate files, again, desktop, airfoil. See, we have 2 separate coordinate files, and you just have to make sure that you are choosing the correct base plane here, the base plane, plane 4. This was the plane we created that was offset from the other plane. Generates, and you have your second 3D curve, which is 1 meter away from your other surface. Okay, and you want to create another surface from your new imported data points. So this is going to be one of them is going to be our root, one of them is going to be our tip. And if you don't want to have, if you want to have a variable chord, you essentially have to take one of the surfaces and do some transformation on it. You come to create body transformation. You can scale it down, you can move it, you can rotate it. What we are going to do here is to scale it, and the scaling origin we want to choose as the body centeroid. The body, let's choose this body. Have to make sure that you are choosing the surface, not the edges, okay? And this is how you can move between the surface and the edges here. Okay, and then apply a scaling term uniform. You can change that to non-uniform. Will give you different scaling factors in each direction. What do you want to do? Keep it simple, uniform, and then generate. You can see the edges here. I don't know if you can see it in the recording, but yeah, you can see the edges here. And this is going to be your new scaled body. Okay. And what I want to do is to create the wing. That's the next step. Okay. You come here, you choose the skin or loft option. Then you want to hold the control to be able to choose these 2 surfaces. Just have to make sure that you click not the edge here, but the surface, and then apply. Okay. When you apply, you just have to make sure that in the materials you just use add frozen. I'm not going to go into the details of why, but there are a lot of tutorials online. If you wanted to know, you can just go there and find out why. And then we want to generate. That's it. This is going to be your new wing. It is not a perfect CAD design. There are like you want it, and if you are doing this and if you are mimicking a real world design, you probably want to move this a little forward to have a straight wing here, depending on the design, of course. But the idea is you can do a lot of operations. Here you have all the boolean operations, all of the body transformation. You can add primitive shapes here, like a sphere, box, and all of those things. A lot of different tools, but I want to keep this short, so I'm not going to go over all of those. And this is essentially what you need for your analysis. There are a couple of people who are or maybe just one project who is going to use who is going to analyze flaps, right? For flaps, you essentially have to import a new airfoil, make it smaller, and then transform it, translate it to another location. For example, a location here on top, right? And create different geometries. If you have any problem, if you are the one who is working on this project and you had any problem creating the two geometries, separate geometries, please make sure to contact me and we'll go over them to you. So we have the wing, but we don't have the air surrounding the wing. So next step is to create that air surrounding the wing. I'm gonna do a box from the from the coordinate systems, and here we want to find the base points. I want to keep the box small, so maybe 10 by 10 by 5. So we want to start from 5, 5, and 5. And I don't see my box anymore, but let's do this. 10, 10, and -5. Let's see what we have done. Yeah, that I should have started the base point from negative. Sorry about this. -5, -5. You want to make sure your box encloses the wing, okay? Which plane are we using here? No, that is actually should be +5. Why are we getting it? Okay, at least we are moving in the right direction. One thing you want to make sure is that these two surfaces are aligned, which is not the case here. I'm getting myself confused. So your x, this is going to be your x direction. Let's do -5 in the x direction. This is your base point, -5 in the y direction. And then the z, you want to do, yeah, +5. So see, right now, it encloses your wing completely. The idea was this is going to be your starting point, which is in the original xy plane is 5, 5, -5, -5, and +5 in the z direction. Then we added +10 meters in one direction, +10 meters in another direction, and -5, moved -5 in the z direction, right? We can actually keep it smaller as well to make sure the number of data points are going to stay below the limit. But if you're using the softwares in the computer lab, you don't need to keep the number of data points, mesh data points below. There is no limit. There is a limit, but the limit is very big. Okay, so we have two shapes here. Here you also have to make sure that it is as frozen, your material. Okay, as you can see, we have the both shapes here. We have the box, the surrounding box. To make sure that your mesh is a good mesh, it is not a bad idea to get a half a circle here. This is what most people do, but I want to keep it simple, so I'm not going to do that. But it is not very hard to do this, right? You just come here in the concept, you just play with this, come here in the create a primitive, just have to create a sphere, and then create a box that starts from here, then unite the two. That's it, through a Boolean operation. We are going to use the Boolean operation so we get some exposure to that. But if you want to make sure your mesh is a better mesh, that's what you want to do. We are mostly interested in the area surrounding the airfoil, so you can also create a sphere that encloses this airfoil, a smaller sphere, and just in the meshing part, just make sure that this mesh is finer here. You have more number of data points, more data points inside this sphere. Okay, so next step is to create the geometry. We need to do a Boolean operation. We need to subtract this geometry, this box. You come here, operation is going to subtract this box, apply, right, and then from the wing. Okay, so you have three options. One is the edges, the other one is your mesh surface. You can actually suppress these bodies here to make sure we are not making any confusion. We can change the names here as well. Let's change this to wing. Since we are in the Boolean operation, we cannot change the names here. We have to make sure we have general, but you can change the names as well. Yeah, so we were in this. See, we can move the body to the big box and the wing. You want to choose the wing, okay, and then do the Boolean operation. So now we have a huge box with a cutout of the wing, right? And we have our geometry. The geometry is complete. We can move on from this. Just close this. It should automatically be updated here. As you can see, the check mark sign. But if not, you just have to click and click on the update, right? So let's go to the mesh now. Double click on the mesh. And just wait for it to open. This is still working, so we're just gonna give it a couple of more minutes. Yeah, this is your box. You can rotate this with holding the middle mouse, the third mouse button, your mouse wheel. You can zoom in and zoom out with the mouse wheel, and you can move the box with the cursors on the keyboard. We have the geometry, one solid geometry. We have the material. We don't need to really do anything at this point in this material. And we have the coordinate system, again, not very important at this point. Then you have the mesh option here. You can add a lot of things to your mesh option. We can insert meshing methodology. Right. When you don't need to do this, but I'm just gonna explain it a little bit. You have to create a geometry, apply. And the methodology, you can do automatic, tetrahedrons, hex dominant, sweep, multi different types of geometries. but we want to keep it automatic at this point. And then you can insert sizing. Again, you have to choose a geometry for your sizing. Different options: element size, sphere of influence. I can add a sphere of influence, as I said. Body of influence, factor of global size, all of these options. We want to keep it simple as well. But our element size is 0.75 meters. That's the largest element size. We want to make this smaller because 0.75 meters is very huge. I'm gonna make it 0.1 meters. Let's do 0.25 because I want to keep it smaller than the limit. And you also have the smallest the growth rate. So on the essentially what's going to happen is that on the locations when you have the biggest shape deformations, like here, you are gonna get the highest concentration of mesh. You can play with all of this. To get a very accurate simulation, you actually want to play with all of this, but I just want to give you an overview, so I'm not going to go over this here. You can of course come to my office and ask any questions, or send me an email and ask any questions you may have. So let's generate the mesh. Hopefully the number of data points is going to stay below the limit. And we have the mesh. The next thing you want to do when working on the mesh is to name the different surfaces. Okay. Again, this surface, you want to name the surface. As I said, this surface is going to be your essentially. This is the where your wings is connected to the fuselage. Right, that's the idea. So I'm just gonna name this wall, and then we can choose the wing inside. Do a change the name here, wing as well. This is the back. This is the outlet essentially of your simulation domain. And this is the top. This is the front. This is going to be your inlet of the simulation domain. And this is, I don't know, I clicked on the wrong thing, sorry. This is your bottom, let's call it bottom. This is going to be your side outlets. All of these are, I don't know if you named the back here. You can check your name selection here: wall, wing, back, top, front, bottom, side. Okay, so we have named all of the selections. So let me actually explain this a little better here, at least try to explain this a little better. The idea here for air analysis here is that air comes in from this side and then can go out from the top, can go out from the bottom, can go up the side, the bottom, but it will mainly go out from the back, right? So we are not in a wind tunnel in the simulation analysis. And but the wing is connected to the fuselage. The fuselage is a huge wall. So think of a very small wing that is connected to a very huge airplane. Not very feasible, but we didn't want to include the whole plane. If you want to do that, you are all, of course, welcome to do so. It will be a great practice for you if you know more CAD. If you are comfortable with CAD, definitely do that. And these data points, these are not only on the surface, these are also the mesh points are inside the three-dimensional model, but we don't see it because of the fact that it is a three-dimensional model. But you can come to the display here, change the display to wireframe, and see all the mesh everywhere, right? So we have the mesh. If you recall, this is a different system than we talked about in class. This is not a finite difference system, it is a finite volume system, but it is essentially the same idea, if you will. We divide the geometry to very smaller points and then calculate the values for those specific points, then calculate the value of a neighboring cell, a neighboring point, using the data from the previous points. Okay, so we have the mesh. Let's close this. We are ready. You just have to make sure, see, we don't have the check mark here. You just have to make sure you click on the update here for your check mark, for your mesh. To get the check mark, you have to wait for it a couple of seconds. If you're doing this on your laptop, I don't know how powerful of a laptop you have, but I assume it is not as powerful as a PC, probably. So all of these may take a lot more time. Keep that in mind. Then we want to come to the setup. Okay. This is the first window you're gonna see when dealing with Fluent, which is the main or the most common fluid flow analysis and the Ansys software in the Ansys package, right? You want to do the double precision. You don't have to, but why not? You can choose the number of CPU cores you have. I'm gonna choose 4. You can actually choose the number of GPU cores you want to use here as well, but we're just gonna keep that to 0. And then let's just start. The first thing it does, this is what you're going to see if you are using Ansys version 2021. The first thing it does is to check your mesh, faces, all of things, as you can see here, and the mesh is done. This is your geometry. Okay. And you get a lot of options on top, you get a lot of options on the side. We're going to use all of these, right? The first thing you want to do is to check your mesh. Okay, here, that's the first. Let's just make sure that the check, we have already done it once, but just want to do it another time to make sure. And mesh is fine. It's not a very good mesh, but it is fine. And then these options goes back to the type of modeling you want to do. Like if you want to do the pressure-based modeling, density-based modeling. If you're doing a compressive analysis, you want to do the density-based modeling. But we are going to keep it simple again. We want to do an incompressive analysis, velocity formulation, absolute, relative. Let's keep this absolute to make it simpler. You can add gravitational force, but we don't need to because we are dealing with air. And you can do a transient analysis or a steady-state analysis. So essentially, transient steady-state analysis assume that there is no changes in each point's value with respect to time. Of course, you are going to start your solution from an initial value, and with each iteration, your value is going to change. That does not signify a change. That does not show a change in time. Right? It change over iterations. Of course, in real world, time is passing for those values to change, but in simulation, we are just going to get to an accurate result, right? We talked about the error analysis and all of those things. But if you want to see changes over time, in the simulation world's time, you want to click on the transient modeling. If your project is on vortex shedding, all of those things, you just have to make sure that you do a transient analysis. But here, we only want to do a simple lift and drag calculation for 0 angle of attack. So we want to keep this at the steady state. Then you come here, you go to physics in your tab, you come to boundaries. We want to define the boundary conditions. Usually what Fluent does is that it defines the boundary condition, all of these, as walls. See, all of these are defined as walls, which is not the case, right? Just we only have two walls. One is the wing wall, and a wall boundary is essentially a boundary where you have a solid, right? Meaning that there's no fluid that can go inside it. The velocity of it, if you have a no slip condition, is going to be 0, okay? But the inlet and outlet velocity, fluid velocity, shouldn't be 0. So we want to change this. You come here to physics, come here to boundaries, click on the boundaries, and then the back boundary, click on the back boundary type. Let's do outflow. We can actually do pressure far field or pressure outlet. All of these three tells us that this is an outlet with different simulations, with different approaches essentially. They mean different things, but they're going to act as an outlet. So let's do, and we want to do the flow rate weighing 1, which essentially means that all of the flow is going to get out of here. Then bottom, again, this is outflow, apply, close, front. Front is our inlet. So we want to make sure that we use an inlet here. And it can be our either mass flow inlets or velocity inlet. I'm going to choose velocity inlet, but you can choose mass flow inlet or any other types of inlet. We want to keep the velocity magnitude. We want to define the velocity magnitude and direction, because you want to change the direction of this flow, right? Based on, you want to change the angle of attack, right? For our simulation here, let's do 10 meters per second, which is very, very small. Keep this in mind that we are in the very low Mach numbers here. And we want to do 0 angle of attack, so your x component of flow direction is going to be 1. If you don't know how to calculate the different angles of attack, essentially if your angle of attack was, let's say, 5 degrees, your x component would have been 10 multiplied by cosine of phi, and then your y component would have been 10 multiplied by sine of 5, okay? So that's it. And in the z direction, you don't need to add any velocity. If you do so, you are going to introduce an angle of sideship. And we haven't talked about this, we don't know what it is, so let's just keep it simple. And apply. Interior solid, you don't need to do anything about this. This interior. Side walls is just y, it is an outflow again. So apply. Top is an outflow as well. Apply. For your wall, wall is wall, and then we have the wing, which is also a wall. So this is for your boundaries. And you can see different boundaries here. We have inlets, internal boundaries. Don't worry about this. Outlet, and wall. As long as you set the correct inlet and outlet, you should be fine. One thing that so this is the boundaries. But then what about the material? The material, we are using air as the fluid material and aluminum as solid, but we are not doing any fluid-solid interaction analysis. So solid is non-important and air is already set. We don't need to change anything here. But if you had to change it, if let's say you are doing an analysis on a submarine, right, instead of an airfoil, just come here, change this, change the material type. They have preset material, but you can also define your own setup, your own material. Okay, so we have the boundaries, we have all of the values here. The next step is to define the model. Whether we want to do a multi-phase analysis, which we don't, because we don't have any like vapor and what do you call it? Vapor and liquid interaction. Energy can be off because we don't do any temperature analysis. But if you want to do the temperature analysis, you just click on this, check it out, and you will do an energy analysis. But then you have to define the temperature boundaries as well. If you are analyzing the effects of temperature on lift and drag coefficient, just make sure you do that. You do analysis. Viscous analysis. We are keeping the velocities to a very low velocity, so I assume we are going to remain in the laminar region. I'm going to move to laminar. If you only want to do analysis on the lift, you just choose inviscid. If not, you choose laminar to stay in the correct lift and drag. To be able to calculate lift and drag, both of them. And what we are going to do, we are going to do two simulations, one with laminar, one with inviscid, and then see the difference between lift and drag calculations in the two. But if your simulation is going to transition from laminar to turbulent flow, you have to choose one of these types of turbulent flow analysis. But I assume you haven't done any turbulent flow studies. You don't know turbulent flow, so just choose one of them and go with it. Okay. We don't have any radiation, we don't have any heat exchanger, we don't have any species, and that's it. You're just going to keep the rest of it as is. And that's it for your setup. Then you go to the methods here, double click on the methods. This is the simulation methods. This is the discretization methods that we are going to see, and like pressure velocity coupling. These are way out of the scope of this course. These are more directly towards the CFD course. Understanding this, so you just want to keep them as is. And then the same is true for controls. Just want to keep them as is. And here, report definition is one thing that you need to focus on. We want to define drag and lift force. Okay, come here, force reports drag. Drag is the force in the x direction, x is this direction, so drag is this direction, so it is the correct direction. We can do the drag force or drag coefficient. We can change here, drag coefficient. Okay. And then we want to report file, we want to report plot to see the evolution of this drag as you move forward. And this is we had to let me edit this. I forgot this part. We have to choose a zone we want to calculate this drag on, so wing. You see how easy it is? Just click on something, you'll get a drag instead of finding the pressure distribution and calculating the drag using that integral. Okay. So you will have the drag coefficient here in your reports. But we are going to add another report for lift. In the y direction, it's the correct direction, this direction, right? Something that you have to keep in mind is that this is the correct direction because my angle of attack is 0. If you change the angle of attack, you just have to make sure that your lift and drag are perpendicular and tangential to your flight path, okay, to your air path essentially. So you have to change these as well. If you don't know how to do these, how to do the calculation, it's a cosine and sine thing. You can of course come to me and we'll do this. So lift coefficient, we want to do the plot, we want to do the file as well. I forgot to choose the geometry. You want to click edit here and choose the wing. And that's it. That's for the monitors. We can monitor the residual value, which essentially it is going to give you the error, the difference between each velocity values at the difference between each calculated velocity between each iteration, right? We want to set the residual value. We want to set the minimum residual. When your solution gets to your minimum residual or the number of iterations you set, you will get the solution. We'll talk about that later. We can add, we can get the drag coefficient plot, lift coefficient plot. We will see all of those in the simulation. Just have to make sure that we do a sub-window view to get all of the analysis we want to get, all of the results, to see all of the results we want to get. And don't need to change anything on the cell register side. So your first is to assign an initial value to everything. I'm gonna assign 0 to everything, gauge pressure 0, everything 0, right? Since our velocity is non-zero, this essentially means that our true solution is going to be very far away from here. So we are gonna need a lot of iterations to solve this problem, which is all right. Okay. And we don't need to change anything here. Then you come to the run calculation part. If you are doing the transient analysis, these parts are going to be your time scales, but this is a pseudo transient setting. We don't need to change anything here. Just check case. And it's telling us our mesh is not very good when you check the case. We already knew that. Change the number of iterations here to, let's do actually 20,000. I don't remember if we set the residual. Let me go here. Let's keep the residuals as is. Don't need to change anything here. That's all right. Okay. Okay. You see the criteria here. Our residual is 1 multiplied by 10 to the raised to the -3. So we're just going to keep that as is. We are ready to run the simulation. We have set everything up. We are ready. Okay. So let's double click on this again. All of these, if you don't know, because you don't see me double clicking, I'm double clicking all of these options to get it on here, but here you just need a single click, right? We could have done all of these through these tabs. These are essentially the same tabs, right? But you can do whatever you like to do. So double click on run the calculations and then click on calculate. This is your residual. See? This is the evolution of lift and drag with respect to each iteration. So since this is a steady state condition, an acceptable solution would be when these get to don't change, when these don't change, right? You can see our velocity residual is coming down very consistently. It is 10 to the -5. As soon as this continuity gets to 10 to the -3, we will have the solution because the rest of them is 10 to the -5. But your drag is oscillating here, which is due to the mesh. So it is possible for us to get the solution, velocity solution, continuity solution, but get the non-correct solution for lift and drag. Just have to make sure that you are clear on that. But if you did that, if you got the non-correct solution for lift and drag, you just have to decrease your residual to a lower value. You see calculation is complete here, but we don't have a steady solution here. So lift and drag, for lift, probably we have a steady solution. We can zoom in. I don't remember how to zoom in. But you can see it has reached a steady solution, which means that we have a correct solution. But this one is still decreasing. It has not become a line, right? For this is lift, right? Okay. So keep that in mind. So this is your results. We have lift coefficient, we have drag coefficient for one angle of attack. We can actually submit reports for forces here as well. Create reports for forces in a text file. And on a wing, let's see, same thing, forces in the X direction, wing, you want to write it to a file, anywhere, it will give you the lift coefficient, and each iteration you want it only use the final value. You can actually double click on this to get the lift coefficient as well. It should have given us the lift coefficient. Then you click on calculate, it will give you the, we should have seen this in this console. Not plot, we want to get the reports. That's alright. You are seeing the results here. We don't need to get the report. And here, if you want to write it to a file, you come to forces. Again, in the correct direction, you write the force. You change this to Y. This is drag, right? You change it to Y. And you will get the drag. We can also do the all types of forces, the tangential force, all of those forces. Let's actually do another analysis, as you can see here, with the laminar analysis, which means that we are already including the effects of friction. For lift coefficient, we are getting a value around 5. For drag, we are getting a value around 1.4. Okay, for 0 angle attack. Let's actually change the solution method that we had here to inviscid and see what we are going to get for lift and drag. You will see the importance or lack thereof of friction calculation in this specific analysis. The first thing you want to do is to initialize again. Okay, let's do this. To bring back to your initial condition and run the calculation now. As you can see, we haven't converged. The solution has not converged yet. But you can see we are essentially in the same ballpark values. It is changing. It has changed a bit, of course, but we are in the same ballpark value. The reason is because of the fact that your pressure is way more dominant here compared to the effects of friction. Okay. In this specific case. But if you want to test it, you can run it with the circle and see what results are you going to get. And that will give you the accuracy of the Ansys modeling, actually. Okay. So I guess that's it for the tutorial. You can report all of your results and then write the report. Hopefully this has been helpful. I'm sorry it went for an hour basically, but you have a very complete tutorial hopefully, and you can of course come and ask me questions if you have any, and yeah, that's it. Have a good day.